We live in a connected world. We as humans are connected with smart devices and social media platforms. Our homes are connected via sprinklers, lights, televisions, appliances, doorbells, and alarms. Cars are connected to their drivers and manufacturers, and in some cases, each other. And industry is connected with machines speaking to each other, sensors monitoring the process health, and artificial intelligence making decisions for optimization. In this episode of the Thermal Review, we discuss how cloud-based monitoring is changing condition-based maintenance in an industrial setting. Welcome, everyone. Marcus, good day. How are you?
Good. How are you doing?
I'm doing well. I'm excited about this subject for today. What do you think about it?
I think it's exciting because I've been in that sort of world for a very, very long time.
Yeah. In fact, I don't believe, Marcus, many know this about you, but you once were a plant manager.
Yeah.
Up to your eyeballs, I'm sure, in plant maintenance.
Oh, many, many moons ago. And I remember having a little stretcher in my office, sleeping there, That happened on several occasions. And it was rough. So I can empathize with folks that are, dealing with maintenance issues, because as we say, the show must go on, and production can't stop. And if something happens, it's definitely panic on to find find the right solution and find a fix and do it quick.
Yeah. Can you share a little more, I guess, history into that background, Marcus?
Yeah, absolutely. So I came over to the United States, as probably folks can figure out. I have a little bit of an accent. I come from Germany. So I ended up here, touchdown in Torrance near LA in '96, and I started working in a textile manufacturing plant and taking care of textile machines from a maintenance point of view, and actually started with commissioning a machine back in the days together with my dad. Actually, his job was deploying these machines. That's how I kind of ended up here. And then when you start wiring up the machine and automating it, you have very in-depth knowledge of the machine, and you absolutely perfect match for troubleshooting any issues. And I did this for a while, and then the owner of the company said, "Hey, what are we going to do if you leave here and the machine goes down?" I said, "Well, you can call us back. We'll come over and we'll fix it for you." And he says, "Well, I have 2 hours to get the machine back up and running based on the output of this machine." And I says, "You have a problem because the flight takes 12 from Germany." And he didn't like that answer.
He didn't laugh, huh?
No. He says, "No, you're going to stay here." And I'm like, "What do you mean?" No, you're staying. I'll make sure you're staying. So that's how I got hired on. And then after a while, I agreed to this deal, and after a while, I was getting bored because the machine was running, because as you can see by the failure curves of new equipment, typically in the beginning you have a lot of little hiccups when you run off a machine. Once the machine is running, it's usually very few problems after the initial startup hiccups and those kind of things. But then, so I got bored. I went back to the owner and said, "Don't get me wrong, but I'm a little bit bored." He said, "The machine is just running fine, and I feel that I'm not pulling my weight here. I'd like to do something else. If you have something else to give me." And he says, "Oh, sure. Why don't you take care of all of the machines?" And mind you, those were like 6 production buildings full of machines, different machinery I've never seen in my life. And I'm like, ooh. So I was sent back to Germany and Italy and Switzerland and Austria, and I got training on all of these other machines. Anyways, long story short, I learned how to troubleshoot all of these machines, understanding how they were working. And shortly thereafter, they promoted me to become the plant manager in that plant. And here I was, 25 years old, and all of a sudden I had 30 people, about 15 mechanics and 15 electricians, across 3 shifts, and they're like, "Here you go, you're in charge. Like, no machine can be down." I'm like, great. So that's why I can really emphasize with folks in maintenance, because anytime any problem was happening, and there were plenty, they would just call me and says, "Hey, you gotta take care of this." The production managers were yelling at me, and I need to run production, or my production just got ruined because the machine stopped, and we can do it all over again. And so that's kind of my insight. So I spent about 3 years doing that, and it's to a degree it's a bit ungrateful kind of a job, because everybody expects you to have everything up and running. It's like, and you cannot always take it personal, but people get very upset, the people that are in charge of production, output, and quality, and everybody comes down breathing down your neck and like telling you to hurry up, not understanding the technical side of things and how difficult it is sometimes to even find and locate an issue, and dealing with all of that. So
Yeah. Well, thank you for sharing that background. I knew this, of course, so that's why coming in today to today's topic, subject matter, I was like, oh, this is perfect. This is right up Marcus's alley. But I don't believe many out there, until now, of course, knew that about you as part of your career. So, when you were running the plant there, I'm sure you were involved, or at least aware of the different types of maintenance programs. There's different methodologies or mindsets, if you will, around maintenance, and
yep.
Maybe we can talk a little bit about those. I've heard these described, and people will use different terminologies, and some will say, "Oh, there's 4 methods of maintenance," and some will say 5 or 6, but and they kind of bleed, if you will, or blend from one to the other as well. There's some crossover.
Right.
Corrective maintenance being one area, preventative maintenance, predictive maintenance, risk-based maintenance, and condition-based maintenance. I've even heard like reliability-centered maintenance and those other terms as well. But
yep.
maybe we can talk about the key ones, if you will, and
right.
what's different about them.
Yeah, there's different methodologies out there, and there's different proponents and opponents out there, and it kind of has to do with the type of equipment that you're running, what you can do, what's reasonable, what sort of budgets you have. Unfortunately, way too often I see people doing the close your eyes and hope for the best maintenance, where it really is the whole like hindsight approach of like, oh yeah, it should be running, and if it breaks down, we'll deal with it later, kind of a thing. The problem with that is that's usually the most costly of all of them, because you have these unscheduled downtimes. You're in the middle of like I said earlier, middle of a production run or something, and then certain processes require you to, shut down the machine properly, run it all out, empty the machine out, redo everything and start all over. So you have to dump a lot of your production sometimes, and it gets very costly. Not to talk about, or not to mention even the upset of the customer, because now you're going to be delivering late. You have scheduling conflicts with your shifts, because the folks that are supposed to run it can't do it anymore because it spills over into second and third shift. Maybe the folks in second and third shift are not as qualified to run it, and all of those kind of issues become apparent once you actually have a breakdown, right? So the whole idea of doing a maintenance program or implementing one is really the one of prevention, right? Because you want to, the more you have this under control, the less of a cost, the less of a surprise it becomes. Very similar to you taking care of your car, right? If you're doing your oil changes on a regular basis, there's less of a chance you're going to have some unpredictable wear and tear issues, with your engine, right? But if you keep running your oil down to the point where the alarm light comes on your dashboard, that's probably not the best way of taking care of your car, right? So those are kind of the different things that are kind of addressing things. So then going back to, let's say predictive maintenance, it's more of a, by statistical knowledge or historical knowledge that certain things will happen at a certain time of usage or after a certain, run cycles, whatever you measure this in, and you can kind of predict and say, okay, that bearing will fail, let's say once a month or once every 3 months or whatever the runtime is and the load is on that bearing. So therefore, let's make sure when we have a scheduled downtime, let's replace that bearing after every 2 months or something like this, because the cost of a scheduled shutdown and replacing the bearing is a heck of a lot less than actually waiting for it to break and other things to get destroyed in the process. So that's kind of the quintessence of a predictive sort of a maintenance. Preventative maintenance is more like the good practice of, let's say, if it comes to lubrication, take your grease gun around and make sure you're squirting a bunch of grease all over the place on a regular basis, just to prevent things from happening without even checking or predicting it. And there's other things, of course, on the electrical side. What we used to do, we would use, once a week, because of the vibration and everything else, we would just take screwdrivers to our switching cabinets and just retighten all the electrical connections. It was a really, literally blister forming job, because you would do thousands of screw terminals and just go in there and give it a quarter turn, because they would get loose because of the thermal cycling and the vibration on the machine all the time. You would just go in there and retighten these things up, because a lot of times you would have failures due to loose electrical connections, and the list goes on, depending on what sort of systems you maintain. It could be a pneumatic system. Make sure that the filtering system is good. Like if you have an oil and water separator or something and an air filter, make sure those are getting maintained properly, right? If you have computer equipment, make sure the ventilation works and you're replacing your filters in front of the vents. Making that, all those little things go a long way if you're doing them on a regular basis. And so they can build up to a critical sort of level, if you will, Condition-based, just to add that, condition-based monitoring is something where you can test a condition of something, right? So it could be a visual inspection. For instance, to put the analogy up there for your car, if you check your tires and you're down to a few millimeters of profile, that's a condition-based preventive maintenance, in a sense, where you can say, oh, you know what, that tire looks pretty bald, I better go and replace it before the belt shows up and my tire blows up, right? So you can do the same thing on machinery sometimes, and there's even sensors for that, where you look at the oil of a machine and you do oil condition testing. And depending on how much sort of rub-off you have or whatever you're testing for, you can kind of figure out when either needs to be an oil change or there needs to be mechanical components replaced because of the rub-off and that sort of thing. So there's a lot of different methods of taking care of your equipment.
Yeah, absolutely. In fact, I think this is a good point to perhaps transition. You started to talk about, you gave the example of condition-based monitoring or maintenance on your car by monitoring the condition, and you used the tire example. When it comes to an industrial setting, there's I've heard them called modalities, different tools or techniques, if you will, for condition monitoring.
Right.
Maybe we can talk about some of those different modalities or disciplines. I've even heard them called as well, because people really do become experts in these areas, these disciplines, to include thermography, infrared inspection, vibration analysis. You've mentioned vibrating, screws coming loose on electrical cabinets, oil analysis, ultrasound. Those are like the big modalities. Maybe we can talk about those, transition a bit now, and how what are the differences? Are there advantages to some of those modalities over others, depending upon the targets in industrial settings?
Right. Yeah. So there's certain physical phenomena that you can use sensors for to measure. And for instance, let's talk about a vibration analysis, which is very commonly done on mechanical bearings, like ball bearings, for instance, right? So the idea is that they're a bearing that's properly mounted, that's running round, should not have a ton of vibration, because the balls that are circulating in the raceway of the bearing, everything is running smooth, it's properly lubricated. So the vibration analysis should have a certain fingerprint, if you will. If you're looking at, you're typically using some sort of an accelerometer or something, that it might be a single axis or 2 or 3 axis sort of a accelerometer that measures essentially vibration of the bearing. So you mount this. This could be a shaft of a motor. For instance, we in our textile plant, we had this massive electrical motor that would drive this compressor, and that thing was under extreme load conditions sometimes, especially when it kicks in the compressor and when there's a lot of load. And that shaft had to be like laser aligned to the rest of it to make sure that there's no torsional forces being created by a misalignment of the shaft, which then would really kill that bearing because it would just kind of grind it down very quickly. And so if you place a vibration sensor on a bearing housing, you can take essentially the vibrational data from it, but the what you have to do, since vibration is typically very high frequent, you have to also sample with your data acquisition system in a very, very high frequency in order to not miss any sort of events there, right? And there's a lot of research that has been done where they can, based on the type of vibration and the noise that a bearing creates, they can actually predict, is it a damage in the outer raceway, on the inner raceway, on the balls? Is it a lubrication issue? Is it something that the shaft is causing? There's a lot of different things that they forensically can tell, but it's fairly complex, and there's also math behind it. And there's maybe a fast Fourier transform to look for certain frequency components. Are they getting stronger? If you have some knocking on, sometimes you can even hear it or feel it yourself. And then you can, based on that frequency pattern, you can start to try to do an early prediction of an issue, essentially. It becomes a little difficult because each machine has its own noise fingerprint, some of which might be normal, some of which might be not so normal. There's applications nowadays where they're using AI, like artificial intelligence, to kind of teach the AI, okay, here's the normal frequency pattern. If you see something deviating from that, let us know, sort of a thing. But the problem with frequency analysis is that if you have, you have 64 bearings to monitor, you got to run 64 RF cables to these accelerometers. You got to mount them all. What are you gonna do with all these cabling in an industrial environment? Now you got to run conduits. It's a quite the endeavor to get this all installed. And now you need some really expensive, high-speed data acquisition system that costs a lot of money to bring all of these channels in and manage the whole thing. And so you typically only see these installed on some really, really high-end, very expensive sort of equipment. So that's one element of doing vibrational analysis on things. Then there's the option to do that thermally and just take a thermal camera and look at the bearing, because the thought here is, okay, if a bearing isn't properly lubricated, or if it's being overloaded, or there's some damage to it, friction increases, right? On one hand, that creates a different sound pattern for the accelerometer, but on the other hand, it also creates a different thermal pattern that can be picked up with a thermal camera, for instance. And so you can use a thermal camera. The advantage there is no cables to run other than the one Ethernet cable or something to the camera, but you can now maybe take a single shot, and you can maybe take 10 bearings in one image rather than running all these cables to it. You plant a few cameras around, and there you go. And now you can say, hey, if this gets warmer than X, now you got to check that bearing. So those are, possibilities, I guess, for these condition monitoring sort of applications there.
How does oil analysis fit into all of this?
So oil analysis is typically, again, they're looking for a chemical sort of an analysis. So there's two things. There's the in-process analysis, where there's a sample device that takes oil samples on a regular basis and analyzes them. And this could be for particles in the oil. It could be magnetically to see any sort of metallic wrap off, or how much is there. which a certain amount of rub off is normal. But I mean, like, is there, at a certain level, can you find a threshold? There's chemical analysis where you can look for oil being getting too warm, being burned. Essentially, you can sometimes a good mechanic can actually smell that. So and then there's the sampling where you're doing it offsite, where you just take a sample, you send it to a lab, and the lab does an analysis from it, like with a mass spectrometer or something, and looks for the components in there, and can kind of figure out what's in it, to what degree, and then based on that you can kind of say, okay, well, that's not normal here, right? It could also be if you have any sort of shaft seals, for instance, and you're separating the lubrication oil from something else. It could be that chemicals are starting to leak into the oil, so that you can start noticing there too, where you would have to otherwise disassemble the whole machine in order to figure out, is that shaft seal still intact? So those are all possibilities there with oil analysis, and those things are more difficult, or those are not really an application for thermography, really. Those are more really a chemical analysis for things there, to do an early prediction of seal integrity inside the machine somewhere.
In our last podcast episode, we were focusing on early fire detection. And in that podcast, we talked about the pathway to ignition. And in some of the content that's available on the Movitherm website, we show a graphic, if you will, and it shows the different sensing technologies, if you will, for early fire detection along that pathway to ignition, where thermal imaging, is at the very forefront, sensing a hot spot before that hot spot can smolder and turn into smoke, which you start to see smoke detectors and different types of smoke detectors being, more effective further down the pathway to ignition.
Right.
Listening to you talk about, a motor, and bearings and things like that, it seems that you could almost have a pathway to failure, if you will, chart for different industrial devices, in fact.
Yep.
Whereas in a motor, it sounds like with the oil analysis, I mean, when you're doing chemical analysis, you're able to detect very subtle changes, maybe very early, if you will, on the pathway to failure, very early. Vibration sounded to me like that may be the next one on that path, where you're able to detect changes in the profile of how that motor moves, essentially. And then maybe thermography or infrared camera technology, at least for motors, comes a little further down that pathway to failure, because you're at that point in time, you're looking for the generation of heat.
Right.
I don't know, does that make sense?
It does. And it's kind of a bit between the vibrational analysis and thermography. Sometimes thermography is earlier, and sometimes the vibration is earlier. It kind of depends on the mechanical design of the machinery on some level. What you also need, though, is with the thermography itself, it really just gives you one indication, and that's heat, right? Now, since you have an image of the heat, let's say you're imaging an entire electrical motor, you can actually see different things. You can see if the very front gets warm and there's a bearing, let's say if it's an asynchronous AC motor or something like this, that basically just has a rotor, a stator, and it has a bearing up front and a bearing in the back, and then maybe a cooling fan. It's usually just popped onto the shaft that while it's rotating, it's cooling itself, and it's blowing air back over the cooling fins of the motor, for instance. We had often failure modes where it was a very dirty environment, and you had a lot of gunk on the fan cover. It was completely clogging up, a lot of lint, because we were working in textile. So there was a lot of lint build up on the fan cover on the back. So the fan wasn't blowing air anymore because it couldn't suck in any air because it was completely clogged up. So now the motor started to run a heck of a lot warmer now because the fan wasn't blowing anymore, or a lot of less efficiency there. And this could go unnoticed for days on end. nobody would pay attention, or the motor is somewhere hidden underneath the machinery somewhere, another cover over it, whatever the case may be. So that could be in a situation where a thermal camera can see like, hey, this motor is getting warmer and warmer and warmer. Like, what's going on here? And it's a simple take a brush and brush off the stuff from the back, that sort of thing. Or we had situations where the fan itself just had slipped on the shaft. It was just press fitted on or something, and it had slipped, and it was just not spinning properly anymore. It was just kind of dragging along on the shaft. Those kind of things. Or you have bearing failure. That's happening quite often as well. More towards the front typically, because there's a higher load on the front shaft of the motor. So you have bearing failure, and if you run this thing to the ground where the bearing completely seizes and fails, I mean, you can burn up the motor, you can do all kinds of things. We had a lot of motors that had to come out, and we had to replace windings, they had to get rewinded. There was a shop that would do rewindings of motors because it was actually still cheaper than buying a new motor back in the days. I'm not sure if that's still the case, but things like that. But you had a lot of downtime all the time. But nonetheless, though, one thing to keep in mind, thermally speaking, yes, there's a lot of information there, but the question is really for a really early detection, because you can run different processes on the machine, right? So the motor might experience different load conditions doing different parts of the recipe of whatever that machine does, because the motor may speed up, it may have to drive some more load. So it's natural to expect a temperature variation of the motor. The question then becomes, okay, is this temperature variation expected? Is it normal, in the normal range, or is it indicative of, hey, there could be something wrong, right? So one thing to separate this would be, okay, is it more towards the bearing up front, or is it really the winding that gets warmer? It could be what we have done often if it's a three-phase motor. If one phase becomes loose, the motor becomes unbalanced. So there's more load going through two windings than compared to the third, and it should be balanced through all three, and that tends to get the motor warm. So the quick indication is like if the motor runs warmer than its specified operating range, it's a slam dunk. It's like, okay, something is wrong. The motor should never run warmer than it's spec'd out to be, because that could really cause burning of the windings and those kind of things. So that's clear. But if you really wanted to catch it earlier, you have to also have knowledge about the actual load condition of the motor, because a higher load means more heat generated, right? So it would be necessary in those instances to actually measure the phase current. If you have a three-phase, we could attach phase current monitors on the three phases, and then we can tell, okay, are all three phases running the same current? That means it's balanced. And if the answer says, okay, that's great, and then how strong of a current is going in, we know what the voltage is, we know what the current is, we can calculate what the total wattage is that the motor is under, the total load. And from that, we can gather, okay, how much heat should we expect, but if the load increases, you see the current increasing and the temperature increasing. And then if you have historical data on this doing a process and it goes outside of those bounds, temperature and current goes up beyond where you're expecting it to be, now we have an early indication of, okay, something isn't right anymore. Either something is jamming up in the machine that the motor is driving. It could be a roller that has its own bearing that are seizing up, or the motor itself has an issue. But either way, you find a way to do kind of like an early prediction there. But it's not quite as simple anymore as just putting a thermal camera at something.
Yeah.
You have that in like if you're pointing a thermal camera on electrical connections, there you can kind of see, oh, if this circuit breaker is under the same load as the one next to it, but the right one, it's a lot warmer, that circuit breaker has either a loose connection or the circuit breaker is getting weak, meaning it has a higher resistance than it should have, and therefore it's producing more heat. So those are things, but you do need to know what you're dealing with in order to design a condition-based monitoring the proper way, so not to create false alarms.
Yeah, no, exactly. Yeah, and we've been talking a lot so far about mechanical systems, but you just touched on electrical systems. And thermography, of course, to me, and I have the thermography background, thermography is like a perfect tool for electrical inspection.
Right.
Just as you hit on, anytime you have an increase in resistance, whatever may be causing that, and you have current trying to flow, you're going to see heat. And then you can use that information to diagnose and hopefully do a corrective action and avoid a problem or a surprise.
Yeah, we also see things, for instance, there's hydraulic pumping systems for certain manufacturing processes, and hydraulic pumps are under an enormous amount of pressure, with the oil that they're pumping, depending on what they're doing. And I mean, again, it's natural for them to run warm, but there's also situations where we had customers where if they're running abnormally warm, they can actually catch fire. They have a situation there, or they can pop a seal, and then the hot hydraulic oil splashes all over the place. And hydraulic oil is a nasty sort of a chemical. You don't want to have that splashing around all over the place. And so those are things, that we have, monitoring applications in.
Yeah. In fact, thank you for bringing this up. This is a great, I think, opportunity or time for us to shift the discussion a bit. We've been talking about, the different types of maintenance. We talked about the different modalities for doing inspection or condition monitoring. The subject here is how cloud monitoring or the Internet of Things or industrial Internet of Things is impacting or changing how folks do maintenance. We've talked about this a number of times, Marcus, but maybe at a very high level again, what is the industrial Internet of Things?
Yeah, so it's the IIoT. It always sounds like I have a stutter, but that's what it's called. Internet of Things is IoT, and industrial Internet of Things is the IIoT. It's just a distinction to say, hey, this is specifically monitoring industrial processes, and in an industrial setting rather than in a commercial or end user sort of a scenario. Other than that, it's essentially the same thing. So with that, now we can put intelligence sensors, like we mentioned, like current sensors and vibration sensors and thermography, or like thermal imaging cameras, and any other sensor, level sensors, whatever you can think of that could help you pinpoint an issue before it happens. We can tie all of these sensors in. I call it sensor fusion, really, because you can bring all these different sensors. There's thousands of different sensors. You can bring all of these things in, and you know what they are typically supposed to measure. And if they go out of bounds, or even go out of bounds with respect to each other, because sometimes it's an interdependency, right? Where everything else, pressure and current and everything needs to go up, and if one gets out of bounds, you're like, okay, that doesn't track the way it should be, or whatever it is. That's where the domain knowledge kind of comes in from the process. And then you tie all of this stuff in, and typically you have some sort of some people refer to as a bridge or a gateway. This is a fancy way of tying this into some sort of an embedded computer. And then it is basically an abstraction layer to communicate on one end, on the edge, basically on the factory floor, to all of these different sensors, and manages the data coming in. And on the other side, it's connecting to the cloud, essentially the internet, if you will, to some server, and pumps all that data up. And then you have a nice cloud interface, on your phone or any other web browser enabled device. And then you typically have dashboards that show you at a glance, is everything in the green, is something in the orange, is something in the red that you need to pay attention to, or it will, essentially on a critical sort of thing, give you a warning or an alarm. But the advantage here is that you can equip your entire plant strategically with these sensors, or at least the critical equipment, and figure out if there's anything going wrong. And it's really just reporting an alarm based on an event, right? So you don't have to look at the screen all day long, other than you have an interest to look at it. But if there's something going out of bounds, it'll notify you. So you have kind of that peace of mind, where before you have to you have to put your maintenance crew on it every time, and do your morning and your noon and your evening round and something, and to check everything and see if anything is out of the ordinary. Instead of that, now have it all up in the cloud, and then something, you have all your little listening devices, if you will, that'll tell you, your ears and eyes, if something is not working properly, and usually with a much higher degree of accuracy than a human eye or a human can do.
It's been interesting to see. You talked a little bit about this, about on edge capabilities or intelligence on the edge. Historically, again, me coming from the infrared space, any type of remote monitoring with an infrared camera would require some type of PLC or some type of computer system tied to a camera. And then we would put that smarts inside that computer to say, if you see this temperature threshold, then do this. If then, you're right, trigger an alarm or send an alert. But pretty advanced computing happening on a computer versus where we are today. Maybe you could speak to a little more about that, about on-edge intelligence and capabilities and how that's changing things.
Yeah. So that's a good point, because the let's call it the old-fashioned way, even though it's still being done this way, but everything is moving more and more cloud-based, and there's challenges, because there's the two topics. There's the big data topic, which essentially is high resolution, high speed, high volume of data, versus the IoT, which is usually low volume of data, low frequency, and event-based. That's how I separate the two, right? So to me, it's really, I like to give analogies. Let's think about the stock market, right? So there's the high-frequency traders that look at every little move in the market, and they need every data at all times, and it's a lot of from hundreds of different stocks and everything else. You need to know everything. Whereas the IoT is basically saying, hey, you should sell stock ABC right now because of X, Y, Z. But other than that, you don't have to worry about the stock market. So that's kind of what the IoT does, right? It's really just letting you know when you need to know. So you can go about your life and focus on the things that matter, while having peace of mind. If something goes wrong, somebody's going to let you know, So, but the problem is sometimes that the sensory input, especially from a camera, is very high frequent and very high throughput. So how do you still that down to something that can be digested, in a much smaller sort of a footprint in the cloud, right? So you need an edge device that kind of goes through that. Either the sensor has certain smarts that can do the processing, let's say on a smart camera, it does it on board of the camera and outputs whatever information you need to output. Or you transfer this to the edge device, some computing device that sits on the factory floor, or you would transfer this to the cloud. But then the problem is you have to typically upload a lot of data. And that's usually not the case in an IoT system. You typically don't pump up a lot of data through the connections, because sometimes we have cellular connections and the data gets expensive quickly, right? And you don't want to necessarily have to rely on the cloud for all of the data crunching either. So that's kind of the difference, if you will, there. And then talking about AI, another subject matter that is becoming more and more prominent is, again, we can either have sensor-based NI, where there's intelligent built-in on a small embedded system that's part of the sensor, that essentially does the analysis right there and lets you know certain output criteria. Or we do this on the edge-based device, a little embedded device that has that smart built-in, and then sends the rest up to the cloud. That's typically what is happening. Sometimes you have also AI stuff happening in the cloud, where you just monitor certain trends and look for certain sort of patterns as well.
Marcus, certainly in this dynamic of today, in the market that we have today, seems like we're hearing about shortages in resources. I'm talking human resources, workers across the board being able to accomplish the job at hand. I mean, right now we're hearing all about what's happening in the airlines.
Oh yeah.
For many years, working in the in this space, I would hear from folks in industry talk about the retiring experts, meaning those guys. You talked about them earlier. They could, smell, well, that oil's burnt. I have a problem here. Or they could literally, take a screwdriver and put their head to a motor housing and say, yeah, we've got a bearing going out. They were just calibrated, and they could whoa, that's a problem. I would often hear from industry, and it was across the board. It wasn't any specific industry. It could be electrical utility, it could be power generation, it could be car manufacturing. But everywhere I went, it seemed like I was hearing about, yeah, we have this retiring expertise, and we don't have a backfill coming in. Take that and couple it with the situation we're in currently, where you're trying to hire and find, expertise. How could a company leverage this capability to perhaps solve some of those problems, leveraging this monitoring and cloud-based monitoring and IoT? Could they use it to plug some of that gap?
For certain areas, for sure. I mean, it's what they refer to as the dying breed these days, right? It's like still I'm thinking my background is like electronic engineering, computer science, so I hear the same thing about analog, versus digital, right? How many people in the electronic industry still understand analog? There's very few people that do. Everything is digital, but the world is analog, so you got to eventually you get into digital, but you have to first understand the analog portion. That's the same thing in terms of condition monitoring, where the folks that have been there for 10, 20, 30 years in that industry, they just have the feel and the sense for it. Like you said, like they just look at something and they almost have a sixth sense developed to be able to do this. And yeah, most companies don't necessarily appreciate what they have until these people do retire, leave the company, or whatever happens. But and it's this stuff isn't being taught in school or universities at all, And I grew up in Germany. We had an apprentice sort of program, like this vocational educational system. They called it the dual educational system, where you would be actually doing your job while you're also learning the job in school. So you get basically parallel. You get this this hands-on experience while you're applying your limited knowledge, and it's like a 4-year program. It's very intense and immersive, but you come out of this program and you're immediately applicable. You essentially have 4 years experience already in the job when you graduate, because you have this hands-on experience with all of these things where you immediately apply the theoretical knowledge and put it in a real-world application. Super useful. I wish the US would focus more on this, and I think they have to, because you just can't take folks right off school and apply them. It takes, we hire folks like this, and they're brilliant young folks, but they still have so much to learn, So even if you find a replacement for your old dying breed person, it takes years before you fill that gap, before somebody can even attempt to step in somebody's shoes, footsteps there. So that's really an issue, and I think a lot of companies these days completely underestimate what's coming down the pipe there. And yeah, so circling back to technology, how can technology help with that is definitely on that condition-based monitoring, or even go a step further and do process monitoring is another one of those topics where it doesn't have to be condition-based monitoring only, or limited to it in terms of if something if the question is something going to break. It's like, what about running a fine-tuned sort of a process to produce good quality? You would need to be able to monitor your process, and partially that's solved with your HMI, your human machine interfaces, that the manufacturer of the machine typically gives you this, or other people look at like a SCADA system or something, where they have the machine processes and something like this. But there's opportunities there, especially when you have a lot of different processes that are strung together from different machine manufacturers, and you want to do kind of like a holistic view. How is my process doing from me feeding in the raw material to getting the finished product on the outside, on the output of the machine, that typically spans multiple process steps that are not covered by an individual or any individual HMI now. It doesn't have the holistic view that walks through the entire process. So you can do that, nicely with IoT sort of solutions as well. It's not a maintenance question here. In this case, it's more a product or a process capability question. Are we making sure that we're producing good product, right? And have good quality, and what are all the parameters that need to stay in a certain range to assure that happens, right? Or you may want to know what's the utilization if you're a manufacturing facility, like let's say you're having a CNC machine running. You want to maximize the utilization. Let's say you have an 8-hour shift. How much of that 8-hour time are you actually spending machining parts? Again, it's not so much a maintenance question. It could be, but it's more of the more I utilize the machine, the more money I make, right? Over a certain period of time, Or is my operator taking a bunch of breaks or not taking the job that serious? You know what I mean? Like there's things you can measure and analyze, right? Why is my second shift producing less output than my first shift? Like, what's going on? Maybe you need to train the second shift better. You know what I mean? There's a lot of different information you can get out of, like the old saying goes, measure and you will improve. So that's what I'm saying. It's the eyes and the ears on the factory floor is really what this whole IoT or IIoT really is.
It's an amazing too. Yeah, when you start to monitor and measure and view what things are revealed, just
right.
like you're talking about here. We need to kind of bring things to a close, and I was hoping we could talk about an application as part of wrapping things up. And I know you sign a lot of non-disclosure agreements, so I'm going to be very careful about going into too many details. But this particular application, what so impressed me was a number of things, one of which it was in a remote locations out in the middle of nowhere. There's a substation, so it's electrical utility. That's just one industry. I'm not revealing anything there. But and it was it was a couple cameras.
Yep.
But because of restrictions, because of the remoteness of this installation, you had to come up with some ways to power things and to run things and connect things.
Right.
In a simple and easy fashion. And I was wondering, can you just maybe describe that without revealing too many details, what you did? A little bit about that application.
Sure. So yeah, it was an electrical substation application. It was actually equipment that was already running kind of in a critical state. So they were already worried about it to begin with. And they wanted to make sure that nothing catastrophic is going to happen. So they wanted to keep a very, very close eye on it. So we built a mobile system that could be moved around with thermal cameras. And there was no way, you'd think substation has electricity all over the place.
You would think.
But there was not a 110 volt outlet anywhere near, because it was all like high voltage and this and whatever. So anyway, the conditions or the requirements there were, okay, it has to be solar based. Luckily we had a lot of sunshine. But what happens at night, because it was a 24/7 operation, so we needed also battery backup. So we had to charge the battery while powering the system. It had to be mobile, and it had to be cellular connected. So it had to be completely off grid, right next to a substation, of course. So we designed and laid out a system like that, where we sized up a solar panel. Made it all mobile, made it very small and easily connectable and everything else. And we calculated the battery usage and everything for our, worst case scenarios, so that we can at least bridge, the 12 hours of no sunshine, if you will. And then even had about 3 days of bridge energy left in case there was cloudy days, which in California that doesn't happen all that often, but just to make sure it stays online. And so we built that, and had full remote access capabilities, and it was a cool system. And
very cool system.
And this was a fairly small one, but we can size that any size we want to. Really, it's just a question of how much solar power and how much battery backup you need.
Yeah. And now all of a sudden, even though it was in the remotest of areas, the customer, wherever they are, as long as they had internet connectivity from any device, computer or cell phone or tablet, they could be seeing the condition of what's going on in that remote area where you had installed. And yeah, it was a very small system. I remember that. Critical. But I think that's an interesting point as well, because you could scale it. You could add to it. Or you could start out very small. So for those in our audience today who are listening, just something to keep in mind. I threw this example of increasing awareness through cloud-based condition monitoring. Really think outside the box. Doesn't matter if it's in the remotest of areas and you don't have electrical power connectivity nearby, or if you need to start very small. That's a possibility as well. But one of the advantages to this cloud-based connectivity, as we talked about even with early fire detection, is that you can start out very small and you can scale and increase these things. And again, all the advantages of having edge capability and cloud capability coupled together and leveraging both smartly, you're able to increase that awareness in an easy fashion.
Yep.
Anyways, thank you for sharing that, Marcus. That was a unique application, and I don't think we revealed any trade secrets by talking about it. So I think we're okay. Well, that does wrap things up today. I mean, we could go on talking about these modalities in much greater depth, IoT, IIoT in much greater depth. But if you have additional questions, we always invite you to come to the Movitherm website and visit our knowledge base library there, which is content rich with information, papers, and video content as well. But that wraps it up for today's episode of the Thermal Review.
Yeah. So thanks for listening. As we discussed cloud-based monitoring and how it is impacting condition-based maintenance in industrial settings.
We hope you join us in our next episode where we will discuss, we're going to shift topics a bit. We're going to discuss different techniques for infrared non-destructive testing and how it's impacting the automotive, battery, and aerospace markets. And I promise you will not want to miss it. So make sure you subscribe to our podcast, The Thermal Review, on iTunes or Spotify.
And if you want to learn more about what we discussed in any of our Thermal Review podcasts, please make sure to visit www.movitherm.com. Thanks.